The sampling distribution of the sample mean. This is a topic that you're going to cover even in an introductory stats course, but it's very important for the reasons I'll give later. Okay, first question is, what is a sampling distribution? Let me give you an example. So we have the random variable x, and let's say it follows a normal distribution with mean mu and a variance sigma square. This is the sampling distribution of the random variable x. Once we know the distribution of a random variable, we know basically everything about it. So that's why here, notice I've got mu, which typically you would call the population mean, as opposed to something like x bar, which is the sample mean, right? And this guy is sigma square, which you typically call the population variance, as opposed to, say, s squared, which is sample variance, right? So it's not done accidentally. I put mu here instead of x bar. So that's the first thing to note. Once we can identify a distribution for a random variable, we know everything about it. In other words, if we wanted to calculate probabilities about it, if we wanted to know its mean, variance, skewness, kurtosis, all these things, we know it because we know the distribution of it. That is if those mean, variances and so on exist, alright? Okay, well, we can sketch this thing, so let's do it. We know that a normal distribution is a bell-shaped curve, so along the horizontal axis is my x's, and I'm going to try and draw a symmetrical bell-shaped curve here. It's centered on mu, and the spread around mu is the measure of the variance. So that's what this guy is, x. So that's what a sampling distribution is. Now, what is the use of a sampling distribution? Well, look, if I know x follows a distribution here, say normal distribution, I can answer questions like this. So let's say use of sampling distribution. I can use it to, say, compute probabilities. For example, here, let's actually write that down. I can use it to compute probabilities. An example of this being here for probability that x is, say, less than some number, like 2. You should be able to answer that. Because, say, as an example, mu is 3 here, you know then that 2 is about here, and then you look for the area in there, and that would be probability that x is less than 2. Okay, using tables you could find that. So that's one use. Another use of sampling distribution is that I can use it to compute confidence intervals. Compute confidence intervals. So in this case I would make statements like, I could say I could find 95% confidence interval for mu is blah blah blah. Right, that's another video on how to do that. And we can use it to do hypothesis testing. Hypothesis testing on the parameter. Okay, that word I've just chucked in there. The parameter being the population parameter I'm interested in here being mu. Okay, so I could say, for example, null hypothesis is that mu is actually equal to 5 or something like that. Anyway, to just get the gist of it is that sampling distributions are very useful, and here are the reasons. They can use it to calculate probabilities of outcomes. It can be used to compute confidence intervals on the parameter. Okay, and we could use for hypothesis testing. So all these things require us to know the sampling distribution of the random variable. So, this is not a pointless exercise knowing that we're going to do today to compute the sampling distribution of the sample mean. Another way of saying it is that whenever you are asked to conduct a hypothesis test or compute a confidence interval, compute probability, you're thinking about, well, what is the sampling distribution of something related to your question. Alright, moving on then, the next question is what is the sampling distribution of the sample mean? And there are two cases here, when the random variables are normally distributed and when they're not normally distributed but your sample is large. Okay, so now we're coming on to sampling distribution of the sample mean. So let's denote x bar. Okay, to get a feel for the result, let's consider the following. I have a random variable x. It is normally distributed, mean mu, and the variance sigma square. And it looks like this bell-shaped curve with a peak at mu. Mu is on here. Right, now we want you to think about the following. See, what this actually says is that I draw loads and loads of values from this normal distribution, say 1,000, and then plot a histogram. I will get such a shape. Okay, well, let's say that I have a random variable. Let's call it x subscript 1, which is normally distributed, mean mu, a variance sigma square. And then I've got x2, which comes also from normal distribution with the same mean and the same variance. So say I've got loads of these. Let's say I've got 100 of them. Now here's the experiment I want you to do in your head. Say from each one I draw a value out. So this will be a little x1, this will be a little x2, so on. So I've got 100 of these little x's. Then what I want you to do is to calculate the average of these guys. So it will be x bar equals to sum of these guys so I get one value here. I'm going to record this value, say, in the Excel spreadsheet, and then repeat the experiment. So I draw another whole load of 100 of these x's, and I compute the mean, and I then also kind of record that, okay? And repeat that many, many, many times, and then picture doing a histogram of your x bars in your head. What would you think about the shape of the histogram? Okay, well, hopefully you'll think in your head that it's going to be normally distributed. Intuitively, you'd imagine it to be so. So it's going to be centered on mu. But how about the variance of the mean? Do you think it's going to be the same as sigma square, bigger than sigma square, or less than sigma square? Intuitively, I hope you're thinking that it is less than sigma square. And indeed, it will be so. It will look something like this. Since the area under the curve has to come to 1, if it's more peakier here, it's going to have to be narrow at the ends, like that. It's not a very good drawing, this. This is then the sampling distribution of x bar, centered on mu, but with a smaller variance. Okay, so what? Well, look, if I ask you what do you think would be a better guess for mu, a single draw x from this thing, or x bar, intuitively people would answer, oh, x bar is probably a better estimate for the population mean, mu, than is x. And it's precisely for this reason that the mean of x bar will be mu, but the variance will be tighter, will be more precise. Indeed, we can show that the result is the following: that the sampling distribution of x bar is normally distributed with mean mu and variance sigma square over n. This is the sampling distribution of the sample mean. In the case that the x's are all normally distributed, and also I'm assuming, I didn't say earlier on, that all these draws are independent of, the outcomes are independent of one another, so the outcome of drawing a value from here is not going to affect or impact the outcome I'm going to draw from this second normal, and so on. So what I want to do now is state the result, and then we're going to go and prove two aspects of this result. So we have here comes the proof now, the sampling distribution of x bar when my x's are normally distributed. Okay, say that I have the random variables x1, x2 to xn. They are independent and identically distributed with distribution, each one distribution, normal distribution with the same mean and the same variance. Okay, then what we can show is that x bar, this sample mean, will have a normal distribution with mean mu and a variance sigma square over n. In other words, it's a better estimate of, it provides a better estimate of mu than does single values of x, because of this guy here, small variance than the individual x's. Right, so there are three things to show, of which I'm only going to show two. One thing to show is that the mean, the expected value of x bar is mu. Why that is because remember, this is just equivalent to saying expected value of x in a distribution, and this guy here is the same as saying the variance of x bar. So that's the second thing. That's another thing, that the variance of x bar is equal to sigma square over n. And finally, that the distribution of x bar is normal. Now, I'm going to prove the first two. This one, since you're doing an introductory course, you usually don't have to prove. You can just do it by you can do it by proof by hand waving, by saying that a linear combination of normals is again normal. A linear combination of, let me say, independent normals is normal. So let's just kind of put this on the side then. See, x bar is equal to the sum of all these x's divided by n. So basically it's a linear combination of the x's, and I've just said that we just state that the linear combination of independent normals will again give something, a new variable, which again will be normal. So that's enough for that. If you wanted to do it properly, you could use the moment generating function of x bar. But these two guys for sure usually what you need to know and be able to prove. So let's go ahead and do that. Okay, let's do the first one. We want to show, let's state what we want to do. we want to show that the expected value of x bar is mu. What do we know? What we know, well, the only things that we can use is in this box. That the x's are IID, independent identically distributed, each normally distributed with mean mu, and the variance sigma square. So we can start off by stating that what is x bar? X bar is the sum of each of these x's divided by n. So let's say that since that is true, we take expectation rules. Now I've done so many videos on the expectation operator, it's dotted all around YouTube. Take expectation of the left hand side, take expectation of the right hand side. N is a constant, it comes out. These x's, they are random variables because each guy is not a constant, because each guy follows a normal distribution. So what does the expectation rule says? It says this: expectation of a sum is a sum of the expectations. I believe some guy asked me before, why does it seem like you can take the expectation through brackets as if you were distributing it through? Okay, the word doesn't. It is because of linearity. So expectation operator is a linear operator. So expectation of a linear combination of something is going to be the sum of the expectation of each component. Right. But what can we say about the expected value of x1? It's mu. It's mu because, how do we know that? Because each of these x's, they're each normally distributed with a mean I expected value of mu. So it's mu. How about expected value of x2? Well, it's also mu, isn't it? Because it all come from normal distribution with the same mean and the same variance. So that's equal to 1 over n. How many mu's are there here? N of them. N mu, n's cancel, done. Great. Now, as an aside, let's just pause a bit then. As an aside, for those of you who have done something about estimation, or estimators, we would say here that x bar is an unbiased estimator for mu. Okay, I'll just point that out to you there. But I don't want this to take over what this video is about, so that's on the side. Good. Next thing, let's go and show that the variance of the sample mean is sigma square over n. This time, we're going to use the variance rules. Next, show the variance of x bar is equal to sigma square over n. I'm going to use the variance rules. The variance rules, like the expectation rules, I've done many videos on how to apply the variance rules, variance operator. So I kind of won't be doing this at a slow speed. Variance of x. Well, because we already know what x bar is, we just can go straight to variance of x bar is equal to the variance of x1 plus x2 all the way to xn over n. Then we're using the variance rules to say that variance of a constant times a random variable, the constant comes out and is squared. Okay. Let's just put it on the side because the variance of a constant, say a times a random variable, is equal to the constant squared times the variance of x. Next, and using the variance rules, I'm going to just write this: variance of x1 plus variance of x2. So it's like a bit like the variance operator, the expectation operator here. Variance of a sum is a sum of the variance. But is it always true? No, because the x's are independent. That's why I can go from here to here. To get you to think back, recall that the variance of x, in general, the variance of x plus variance of y is equal to what? The variance of x plus variance of y plus 2 times the covariance of xy. Okay, but if x and y is independent, we know that the covariance is 0. So that's why all the covariances here have disappeared. In other words, when these x and y's are independent, the variance of the sum is just sum of the variances. And I'm just doing this but for many, many more variables, n of them. Continuing on, what do we know about the variance of x1? It's sigma square. Because each of these guys, x's, has a normal distribution, mean mu, and a variance of sigma square. Again, it's going to be the same for all of them. How many do we have? We have n. So we go n sigma square over n square, which is equal to sigma square over n, and we're happy. Now let's look back over our result here. Okay, let's look back at our results. Sampling distribution of a sample mean when x are normally distributed is this. Now in my proof, let's kind of try to understand our proof a bit more in detail. Have I, for the expected value of x bar or the variance of x bar, have I anywhere in that proof used the fact that the x's are normally distributed? In other words, do the x's have to be normally distributed for this to hold and for this to hold? Okay, I bring that up because a student the other day kind of just brought that question up, which was excellent. You can see that normality assumption has not been used at all. In other words, whatever the distribution is of x, this is going to hold. If x is Bernoulli, if x is Poisson, or if x is anything, expected value of this x bar is going to be the mu. And the variance of x bar is going to be the variance of x over n. So, where does normality come in? It comes in the third step. Distribution of x bar is normal. And as a hint for what's to come, I could even say exactly normal. Normal for sure, not exactly normal. And let's see what else we can spot. For the expected value of x bar equal to mu, have we used anywhere that the x's are independent? No, because I haven't written so on any lines here. In other words, this holds irrespective of whether the x's are independent or not. How about so for the expected value of x bar, we don't need the independent. How about identically distributed? Yes, we have used that because, well, to an extent we have used that because we used the property that the means are all the same. For the variance, have we used, which part of IID assumption have we used? We've used independence on this line. Identically distributed, we've used the part of that where to say that the variance of each of these xi's are the same. So there you go. So I'll let you look at that. I have yet to do the case that the x's are not normally distributed, and I'll continue with that in the next video.